Okay, so today we're going to have a wee look at equilibrium and how it's affected by the temperature. First off, we need to do a wee reminder to remind us what exothermic and endothermic mean. So exothermic is a negative enthalpy, so delta H equals negative. That's a negative enthalpy, and that means that the temperature of the reaction, the mixture around the experiment, would increase, so it gives energy out. Endothermic is a positive enthalpy, delta H equals positive, and the temperature decreases. That means it takes energy in. Okay, so let's look at and see how temperature can affect equilibrium. For any equilibrium questions about temperature, the question will tell you the forward reaction, if it's endo or exothermic, and you'll be able to tell that by the fact of it saying delta H equals plus or delta H equals minus. So let's take this one for example. This is carbon monoxide reacting with hydrogen, and you'll be able to see that delta H is negative. That is for the forward reaction, so that means that the forward reaction is exothermic. That also means that the reverse must be the other way. So the reverse is endothermic. Because if you wrote that the other way, then you'd have to change the sign. So that means it would be endothermic, it would be plus. So let's look at what happens when the temperature is increased. So we know that because of Le Chatelier's principle, if you do something to an equilibrium mixture, then the equilibrium mixture will change to counteract the change that you have done. So if we increase the temperature, the equilibrium will move in order to decrease the temperature. So we'll cancel out the temperature change. You've increased it, it's going to make it go back down. So it will move to the endothermic direction because that is going to absorb energy in and reduce the temperature of the experiment happening round about it. If you decrease temperature, what's going to happen is the equilibrium will move to heat it back up. So it's going to go to the exothermic reaction, the side that's exothermic, because it is going to give out more energy and it's going to replace that lost heat energy. So we'll move in the exothermic direction. So the exothermic reaction would be favoured. So let's look at this one here. And we're going to watch a short video on it and you're going to be able to see this actually happening. But what happens is we've got dinitrogen tetroxide, N2O4, forming into N2O2, 2NO2. This is positive, this is endothermic. And what we're going to be able to see is we're going to see how that would happen. So actually what you'll be able to see in the video is you'll be able to see that the mixture is brown at room temperature. If you put it into something that's cold, then it's going to want to make the energy increase to counteract you making it colder. So what's going to end up happening is for this side, the cold, the exothermic is favoured. So it's one to go to the exothermic reaction. So actually 2N2O or 2NO2 N2O4, that is actually delta H negative. So N2O4 is produced more. So what's going to happen is if you cool it down, the exothermic reaction is favoured. If we swap that about and change the sign, then that shows us that N2O4 is favoured. So the reaction is going to produce more of that because that's exothermic. It's going to produce more heat and it's going to cancel out the fact that you've tried to make it colder. If you do it the opposite way and you're going to put it in hot water, then what's going to happen is it's going to move to the endothermic side, which is the reaction that's shown above. So we'll go hot. That's going to be endothermic is favoured. The reason that's favoured is because that's going to absorb heat energy. So that's going to absorb the heat energy of the hot water, and that's going to reduce the temperature to bring back that equilibrium mixture. So that is the reaction above, N2O4 to NO2, and that's delta H positive. So that is going to produce more NO2. That's going to be the brown colour, because NO2 is brown, and then this is going to be this colourless. And we'll see more colourless. Because it's an equilibrium, there will still be some nitrogen dioxide in there, but it's going to be more colourless than the one at room temperature or the one at the hot temperature. What we're going to do is we're going to watch a video of this so we can actually see it in person, see it a lot clearer.
Nitrogen dioxide is brown and produces the colour of the mixture of the two gases which are present in this equilibrium. Liquid nitrogen is used to cool the mixture down to temperatures approaching -200 degrees Celsius. At this temperature, the equilibrium is shifted completely in the favour of only dinitrogen tetroxide, which is present as colourless solid crystals. The mixture needs to be heated to temperatures in excess of 150 degrees Celsius in order to shift the equilibrium to the extent where effectively only nitrogen dioxide remains. The gas would then appear almost black. To do this in this thin-walled glass vessel would, however, be hazardous.
One last point we're going to look at today is how catalysts can affect the position of equilibrium. Well, actually what you'll find is the use of a catalyst will speed up both the forward and reverse reaction, but it doesn't actually have any effect on the concentrations of reactant and product, and therefore doesn't have any effect on the position of equilibrium, but allows it to be achieved sooner. The reason for this is if you can imagine the potential energy diagram, if I draw the uncatalyzed reaction and then draw the catalyzed reaction here as that kind of dotted line, then you can see that all that's changing is the activation energy, and therefore the rate would increase. But if the reaction is at equilibrium, then all that's going to happen is the actual rate is going to increase, but the fact that they're at equilibrium means that the actual rates of the forward and reverse reactions are the same, so they're just going to be the same but faster. Hopefully that makes sense, and if you have any questions at all, then you can get in touch with your teacher.